The discoveries of the James Webb Space Telescope have sabotaged the case for the theory of prehistoric cosmic detonation. The James Webb Space Telescope has recently conveyed an exhilarating revelation that is sending shock waves through the universe of physical science. Through a single stunning picture, it has annihilated long-standing discussions, leaving researchers shocked. The time of hypothesis is over, as Webb's most recent catch is both outwardly charming and a game-changer that vows to alter our view of the real world. What red-hot discussion among researchers has this picture definitively finished? And in what ways is the staggering picture caught by the James Webb Space Telescope reclassifying how we might interpret the universe? Go along with us as we dig into why James Webb's discoveries are stopping discussions in material science. With a breaking picture, the major issue with astronomy is that researchers can't come to an understanding about how old the universe is or, on the other hand, how fast it is growing. This unanswered peculiarity has confounded researchers across ages, driving them to lead different investigations to find answers. Cosmology is the field of research that focuses on getting to know how the universe was made, how it is set up, how it has changed over time, and eventually how it will end. This field has seen significant improvement in the past 100 years. The now accepted cosmology model, the theory of prehistoric cosmic detonation, suggests that the universe has been expanding from a very hot and thick introductory state for about 13.8 billion years. This development is measured by the Hubble constant, which shows the speed at which the universe is extending. However, estimations of the Hubble constant are not direct. Measuring the Hubble constant can be broadly classified into two groups: local measurements and early universe measurements. Local measurements involve the investigation of galactic bodies. For instance, Cepheid variable stars and type Ia supernovae act as standard candles to gauge the Hubble constant. Because of their brightness, astronomers can measure how the universe's development influences the velocities of these objects to find their distances and, in this way, compute the Hubble constant. The second group is the measurement of the early universe. Researchers use observations of the cosmic microwave background, CMB, the luminosity of the Big Bang found during the 1960s. The CMB shows the microwave radiation of the early universe when it was just 380,000 years old. By measuring the minute temperature and polarization variations transmitted by the CMB, cosmologists can lay out the age of the universe and its rate of expansion. But here's the issue. The results of these two methods do not correlate. The outcomes from local measurements affirm that the universe is growing faster than what we estimate based on CMB data. Due to these differences, researchers have been striving to uncover the reasons behind the results. Further research is being conducted to learn more about the mysteries of the universe. As things stand, the difference in estimations shows that there is either new science we have close to zero insight into, or errors in one or both ways by which we are measuring things. Because of the James Webb Space Telescope, we can see into the dim universe clearer than at any other time before. The telescope can show the smallest and most distant components, planets and galaxies we wouldn't have thought possible to observe due to its capacities. Researchers normally believed that data from the JWST would help us definitively ascertain the Hubble constant. However, the first wave of data has astoundingly made matters more complicated. It has provided us with new insights that are not consistent with what we assumed we knew. Might this data eventually lead to a new hypothesis and upset how we ponder space? If this is the case, we may have to reassess how we interpret how the universe works. For example, we may find particles and forces that have never been observed, or it could mean that dark energy, a previously unexplored world factor responsible for the accelerating expansion of our universe, needs to be reevaluated. So far, the ways we think about space have evolved as we continue to discover new things. For instance, in 1965, when scientists discovered the cosmic microwave background radiation, it strongly supported the idea of the Big Bang theory. Before then, researchers believed the universe was eternal and constantly expanding at a uniform rate. However, new evidence showed that was not true. Additionally, when we found out toward the end of the 1990s that the universe was expanding at an accelerating rate, it further changed our understanding. We discovered dark energy and its effect on the universe's expansion. Thus, every time we learn something new, we question whether it fits into our current framework. If not, we develop new approaches to better understand the universe. In this regard, The issue we are facing in cosmology today could lead to the discovery of the most profound answers about the universe. While the issue is challenging, it is also exciting as it forces us to develop more advanced tools to explore space. This cosmological challenge also unites the scientific community from various nations, as each researcher wants to learn more about the universe. Above all, it shows that science is constantly changing and developing as we dive deeper into space. Alongside the Hubble tension, there is also a concern known as the S8 strain, which relates to the spatial distribution of matter in the universe. This can be used to draw an initial image of the universe and see how it has developed. Space experts refer to this phenomenon as unevenness, as there are areas of space where galaxies are tightly grouped, while other regions are sparse. Researchers will use various techniques to measure this knotty distribution, one of which is checking how light from distant galaxies gets bent by the gravity of large objects, such as galaxy clusters. This bending, known as gravitational lensing, provides us with a way to investigate where dark matter is, as it is invisible and does not emit light. Specialists also use the cosmic microwave background, CMB, a glimpse from the beginning of the Big Bang. This light has been traveling for approximately 13.8 billion years, bearing news from the early universe. Through CMB analysis, physicists can interpret how the universe was knotty in its infancy, which should match the observational unevenness of the universe at present. However, here's the catch. These results also don't align with the CMB's unevenness. The non-circular gravity distribution model suggests that the matter distribution at the early stage of the universe was more homogeneous compared to what is observed with gravitational lensing. As such, we can infer that there is something else we are not considering in the explanation. This takes us back to the concept of dark matter. What exactly is dark matter, and how does it work? The truth is, the issue remains unanswered. However, all hope is not lost, as the James Webb Space Telescope, JWST, is set to rethink the field of astronomy with its exceptional high resolution and sensitivity. The telescope will look at the early periods of the universe and research the first galaxies and stars that formed. This makes it possible to improve estimates of cosmic expansion and matter distribution. These basic questions will require precise observation and potentially new approaches from a theoretical perspective to figure them out. Whether the end result is more significance for dark energy, the discovery of entirely new physics, or even gaining a better understanding of dark matter's behavior, the implications will be sweeping. Handling the mysteries of the universe is like solving a billion-piece puzzle while blindfolded. Scientists are like meticulous detectives, focused and obsessed with solving these mysteries. The latest effort, known as Project Flamingo, is proof of NASA's increasing enthusiasm for scientific investigation. Utilizing one of the world's most acclaimed supercomputers, located at Durham University in England, Project Flamingo is an extraordinary accomplishment in computational advancement. It costs more than 50 million hours of computer time and features 30,000 processors and counting. The project highlights the academic community's determination to explore the universe fully, with a particular focus on dark matter. Dark matter, the mysterious substance that neither emits, absorbs, nor reflects light, is believed to exist due to its gravitational effect on visible matter. Its elusive nature continues to fascinate scientists. However, the methodology of Project Flamingo differs from previous simulations. It includes all possible types of cosmic components, from galaxies with the most unique gas content to stars and black holes at the center of the universe. Through such a comprehensive approach, the continuous change in our understanding of the universe has been mapped out from a basic milestone sketch. The motivation behind ambitious projects like Project Flamingo is clear: to explain cosmic conflicts where the measurements appear flawed and do not fit into the structure of the universe. This discrepancy in measurement suggests a fundamental misunderstanding in our current understanding of the universe's operations. If these measurements could be compared to musical genres, they are like jazz and classical, each having its own technique though still related. Flamingo attempts to merge these different perspectives and refine our individual impression of the universe. However, despite its complexity, the vast tension persists. This strain continues to exist as a humbling reminder that we have yet to solve much of the mystery that surrounds us. The universe seems reluctant to reveal its secrets to us. But just like that, As we add each new data point and simulation model to our toolkit, such as Flamingo, an increasingly vast new universe opens up with new challenges to address. That is a never-ending mission, where each answer leads to more questions, revealing an entirely different layer. It shows us that the nature of our curiosity to unravel the universe's mysteries is complex and ever-changing. Since Edwin Hubble made his groundbreaking discovery of the expanding universe in the early 20th century, the pace of our understanding has been extraordinarily rapid. Scientists are constantly making new discoveries about the dynamics of the cosmos, such as the Big Bang Theory, dark matter, and dark energy. They have explored the universe by studying the cosmic microwave background and carefully recording the positions and speeds of galaxies with ever-increasing precision. Each of these achievements is like acquiring one more key piece of the enormous puzzle. This has led to a drive to learn and strive for a greater understanding of the universe. Indeed, the universe is cloaked in mystery, and it can be dangerous to uncover its truths too quickly. With every scientific step, researchers propose refined hypotheses, altered models, and more precise questions. The theory posited by the Big Bang Theory was once highly controversial, but is now considered a major part of scientific knowledge. Similarly, dark matter is no longer a speculative thought but an undeniable key element of our astronomical puzzle. The discovery of dark energy, an unexplored cosmic force driving the universe's expansion, was a late 20th century revelation and is now one of the fundamental building blocks of our understanding of the universe. Let us now explore the various ways researchers have attempted to solve the conundrum of the universe's expansion over time. They have worked tirelessly, yet some of the pieces simply haven't fallen into place. In the past, it was commonly accepted that every object overhead, from the sun to the stars and all the planets, revolved around the Earth. This geocentric view was challenged by the likes of Copernicus and Galileo, who held that the Earth and other planets orbited the sun, introducing a revolutionary perspective. Fast forward to the 20th century, when Einstein introduced a new revolutionary view of the physical world. He proposed a model where existence is not made up of isolated substances but rather a four-dimensional structure called space-time, where everything is interwoven. His discoveries gave the universe a dynamic nature. In 1920, Hubble's observations revealed that galaxies were moving away from each other, showing that the universe was expanding. With this reality, researchers formulated the Big Bang Theory, which suggests that the universe arose from an initial singularity and has been expanding ever since. The possibility that gravity would eventually end the inflationary cycle was accepted. However, Flamingo faced challenges in reconciling the clumpiness seen in the CMB with that in the local universe. Errors persisted between the universe's expansion rate and the distribution of matter, leaving cosmologists searching for explanations. Some predict that new physics and laws beyond our current understanding will be necessary to explain these inconsistencies, while others believe our measurements or understanding of dark energy may be flawed. This attention is a classic example of history repeating itself, with the universe itself serving as the central mystery. To summarize, the capabilities of the latest telescopes and advanced simulations have barely resolved the puzzle. We are now at the edge of the cosmic precipice, where the unknown is hidden. Yet the endless quest for knowledge is one of the wonders of science. Every question opens another door to the infinite search, and with every trial and simulation, we move closer to understanding the universe's vast mysteries. The James Webb Space Telescope, with its advanced capabilities, has provided us with incredibly sharp images and data that add layers of complexity to existing tensions in cosmology. It uncovers galaxies that appear more scattered than our current theories had predicted. Despite ongoing efforts, including elaborate simulations like the Flamingo project, intended to integrate both normal and dark matter impacts, there remains a discrepancy. Flamingo aims to reconcile our theoretical models with observational data, but the universe continues to be surprisingly resistant. So where do we stand now? Our models of the universe are undergoing significant challenges, possibly signaling a paradigm shift, where our theoretical foundations may need to be reassessed. These challenges are not accidents but rather signs, guiding us toward a deeper understanding. Every discovery is added to another, upon which researchers refine their ideas or hypotheses. Each new tension or inconsistency offers some clue that science and our comprehension of the universe must be corrected. The steps of the universe change like no other, with the details being shaped by some strange force, physics. Despite the many complexities involved, there is a persistent desire to explore and understand what we have, keeping us on the path of discovering new mysteries about the universe. To approach the edges of the seemingly endless universe, where consciousness becomes blurred and ambiguous, is to face conditions that challenge us to imagine new ways and concepts for understanding. Each new observation that defies our model serves as a hint that could lead us to new physics, offering new explanations for the fundamental workings of the universe. The essence of science lies in its self-correcting nature. Every revelation builds upon the last, and each anomaly or tension prompts us to refine our theories and our understanding of the universe. The scientific investigation of the universe remains an ongoing endeavor, driven by the advent of cutting-edge telescopes, increasingly refined simulations, and a community of dedicated researchers focused on uncovering its secrets. The universe isn't just a wilderness. It is the ultimate puzzle, and solving it represents one of humanity's most magnificent and exhilarating challenges. As we embark on this cosmic journey, it is important to stay curious and engaged with each new discovery and understanding. We edge closer to grasping the wonders of the universe. The way forward is sure to be filled with surprises, each offering a glimpse into the profound depths of the cosmos. Each discovery brings us closer to addressing long-standing questions, such as, what is the universe, and what is our place within it? Looking forward, the possibilities in this cosmic venture are endless. The information we have gathered may reveal new celestial events, uncover a deeper understanding of dark matter and energy, and even show proof of extraterrestrial life. Advances will continue to grow as we explore space and navigate the vast design of the universe.